This video is going to cover determinacy for beams and frames. Our equation is simply R is something, some type of inequality, to 3 times n. R being the number of reactions that we have going on in the entire beam and frame, and n is the number of members that we have in our beam or frame, different members. So if we have, for the inequality, we pretty much have 3 options. We have a greater than, an equal, or a less than. So obviously the one we're shooting for is equal. If they're equal, then the number of reactions, the number is equal to 3 times the number of members. This is statically determinant. So that's what we're hoping for, is that the whole thing is determinant. And then to remember which one is unstable and which one is indeterminate, we want to think about what's the situation in terms of the reactions. If we have too many reactions is indeterminate. And if we don't have enough reactions, then our beam just kind of walks away, and that's unstable. So we're just going to do a few examples to try and see how this goes. So all we have to do is count the number of reactions and the number of members. So for reactions at a pin, we have vertical and horizontal, so 1, 2. And at another pin, we have another vertical and another horizontal, so 3 and 4. So number of reactions, 4. And we want to know what this is compared to 3 times the number of members. So how many members do we have? Well, this is one solid thing, so this is one solid member. That's it. There's no joints there, no hinges, no nothing. It's just one solid beam. It's in a nice kind of U shape, or in shape, but it is what it is, right? It's just one solid member. So 4 is definitely greater than 3 times 1, so this is indeterminate. Now, usually we also want to find how many degrees of indeterminacy we have, and to do that, we're simply going to take the number on the left, which is 4, and subtract the number that we have on the right, which is 3, and we're going to find that that is 1. So we are 1 degree of indeterminacy. Okay, so that's really simple. Let's go on to another one over here. We have a fixed end, so that's 1, 2, 3 reactions, right? Vertical, horizontal, and a moment. 1, 2, 3 reactions. We have a pin. That's 1, 2 reactions. And then we have a couple hinges here. These little bitty dots are hinges. So a hinge has a vertical and a horizontal, so probably should have kept numbering these things. So 1, 2, 3, we got 4 and 5. This is 6 and 7. Then we've got, again, vertical and horizontal, so we've got 8 and 9. We have 9 reactions. And we want to know how that is compared to 3 times the number of members. And we have 1, 2, 3 members. And 3 times 3 is 9, so this is equals. So this is a determinant structure. Nice and exciting. So we'll do another one. Here we have wonderful 3 rollers. So rollers, we have reactions only in one direction. Got 1, 2, and 3 rollers. Then we have, of course, our little hinge over here. We have a vertical, that's 4. We have a horizontal, that's 5. So we have 5 reactions. We want to know how many members we have. We have this really one long member. He doesn't stop at the roller. He goes all the way across, and then a second member over here. So that's 3 times 2. That's going to be less than, so that is unstable. That's unstable. There's actually another reason it's unstable, but in terms of the equation here, It's just simply we don't have enough reactions going on to prevent this thing from falling apart. So in terms of frames, there's only really a big thing going on that changes them from effectively what you just looked at. The ones before were technically frames. But we want to look out for when we have the situation here of a closed loop. And a closed loop is when you have this kind of going on in here. You've created a box inside of your members. And so on the outside, you might think, well, in terms of reactions, we've really only got 1, 2, and 3, right? And then in terms of members, well, it's one giant member, right? One solid piece. So that really doesn't seem that bad, right? In terms of our situation, we've got 3 reactions, and we've got 3 times the number of members, which is 1. So you're like, oh, this must be determinant. And that's actually not the case at all. That is not how that works. Instead, because we've formed a closed loop, what we need to do is break it up. So what we're going to do is actually cut this member right in half. We need to kind of open up our loop here. So we are going to open up our loop. And when we open up our loop, we're actually going to have a few more reactions. So in this little spot, we're going to have external reactions, right? This is effectively a fixed end because it's connected to the other guy over here. And same thing. We've got the 3 forces. And of course, since it is technically a fixed end, they're all equal and opposite. But how this works is that we're going to treat each set of these as one set of 3 reactions. So this guy is 3 reactions and this guy is only 3 reactions. Because they are equal and opposite, those are only going to count for 3 each. So we have 1 vertical, 1 horizontal. Then we have another vertical over here at the roller. And then we have the 3 and 3. So in terms of reaction forces, we have 3 plus the 3 plus the other 3 for that one and that one. So we have a grand total of 9 reactions going on here. And we want to know if it is unstable, stable, or determinate or indeterminate. So now we got to count our members. Because we broke it open, we've got a member on this side and we've got a member on the other side. So we've got 2 members. So 3 times 2. Well, that's only 6. So technically this is indeterminate. And by how many degrees? Well, it's 9 minus 3 times 2 is 6. It's 3 degrees. 3 degrees of indeterminacy. So whereas it looked pretty fine to begin with, it's not actually fine. And this is really only something that applies to these closed loops. If you look at a frame, you could break it up every single time. But remember, every time you break a member, you now have 2 members and 3 more reactions. They literally balance each other out. So you could come back here and, break open another one of these, say right here if you really wanted to, and you could create 3 more reactions and 1 more member. It would cause the same thing to exist. So really the special case is when we have closed loops. Those closed loops create indeterminacy for us in this case.